Great. So today I want to talk about the Lichtenbaum-Cullen property, and there's really a lot to say about it. And the the thing I want to emphasize today is really if you assume this Lichtenbaum-Cullen property, why does that let you get quite far in like why is that sort of a key ingredient in the disproof of the telescope conjecture? So I'm not gonna explain how to prove the Lichtenbaum-Cullen property. I'll try to say something about that next time. But I want to explain sort of why it's important and why a lot of the proof hinges on that. So, um, so let's recall one of the main things that was necessary for this proof of the telescope conjecture. So we wanted the following square. So we have the homotopy groups of BPN, which is our ring spectrum. We took the fixed points by this Adams operation, and then we tensored with the telescope of a type n+1 complex. And then we had this co-assembly map that sort of compared whether or not TC preserved this limit of taking the Z fixed points. And the point was that if you prove that this comparison map is not an equivalence, then you've disproven the telescope conjecture because this map is the cyclotomic completion map. And we saw last time that there's a slightly different map, which is easier to show as non-equivalence, which is the same thing, but you replace the action. So this was the action of some Adams operations, which I haven't really described very much but there's some non-trivial action on this ring. And the point was that in the case that we replace this action with a trivial action, it's a lot easier to see that this map is not an equivalence. And so what I want to tell you today is how this Lichtenbaum-Cullen property is sort of the key property that allows you to replace the action with the trivial action, um, thereby allowing you to check that this map is not an equivalence. So we wanted to replace this map with the sort of map coming from the trivial action, which we saw last time is easier to show. It's not an equivalence. Okay. So this is the square. And yeah, so the claim is that the key property to prove this is the Lichtenbaum-Cullen property. And I'm going to shorten this to LQ when I define it. So, okay, so what is this? So here's sort of a first definition of what it is. So you say that R satisfies the Lichtenbaum-Cullen property of height n if the following is true. So you want THH of R to be bounded below. This isn't really the main part of the condition. You want the key thing is really what I'm about to say next, which is that you want for all and you want that for all X, which are connective cyclotomic spectra. So cyclotomic spectra whose underlying spectrum is connective. You want the mapping spectrum in cyclotomic spectra from X to THH of R tensored with this type n+2 complex. You want this to be truncated. It's truncated. In other words, doesn't have higher homotopy groups beyond this finite some point, beyond some point. Okay. So this is the Lichtenbaum-Cullen property. Okay, so let me maybe give you some examples of or I'll give you some examples of what this entails. So for example, you can take X to be the sphere, and then you learn that maps from the sphere into this is truncated, which is the same as TC. So taking map X to be the sphere, you learn that TC of R tensored with a type n+2 complex is truncated. Okay. And then I'll mention one more thing that you get out of this, which in some sense is everything. So if you recall last time, I defined this funny cyclotomic spectrum, which I called LP infinity of the sphere, which was sort of the sum over k greater than or equal to 0 of sphere to the t mod Cp to the k. So sort of the sum of these spheres, and there was the cyclotomic structure that was sort of shifting one to the next one. And so this is some cyclotomic spectrum, and maps out of the cyclotomic spectrum has a name. So maps from X to THH of R, or really to any cyclotomic spectrum, it's called TR. So maybe I'll just do it for a more general cyclotomic spectrum. So if you have maps from X to, sorry, not from X, maps from this cyclotomic spectrum to Y in cyclotomic spectra, this is called TR of Y. And so what you also learn is that TR of R tensored with a type n+2 complex is truncated. Okay, and it turns out that this is essentially this is actually good enough. This is in fact equivalent to this condition, and that's because of a result of Antio and Nicolas. So Antio and Nicolas show that they essentially show that this cyclotomic spectrum, it actually generates the category of connective cyclotomic spectra um, uh, under colimits and extensions. And so what that tells you is that there's a way to reformulate this Lichtenbaum-Cullen property as follows, namely, there's a T structure. So you can define the sort of co-connective or n co-connective cyclotomic spectra to be those cyclotomic spectra such that this TR is n truncated. So n truncated. And what you see from the result is that the connective and co-connective cyclotomic spectra form, they in fact form a complete T structure. On cyclotomic spectra. Okay, so whether or not your spectrum is connective or TR is co-connective is a reasonable measure of connectivity in the category of cyclotomic spectra. And so now we can reformulate this Lichtenbaum-Cullen property. So equivalently, we can say that R satisfies the height n Lichtenbaum-Cullen property if and only if THH of R is bound below and THH of R tensor, this type n+2 complex, is bounded above in the cyclotomic T structure. So this means, i.e., in this sort of n-connective cyclotonic spectra, n-co-connective cyclotonic spectra for some n. Sorry, I should probably give this index a different name. Okay, so this is just the reformulation of what the Lichtenau non-pulling property is, and it's really saying that it's some kind of truncated, it's some boundedness property of THH of your ring. Okay, but the question I really want to answer today is, why is this relevant? Why does this help us prove this kind of square that we wanted? And so the first thing I want to point out is that that the square above that we're trying to prove is actually, it's quite subtle for the following reason. So it's not the case. So the square above, if you look at it, it's a square which has isomorphisms at the level of homotopy groups. But these isomorphisms at the level of homotopy groups don't actually come from an isomorphism at the level of spectra. And why is that? Well, in fact, for example, if you look at TC of this BPN fixed points by Z, and you tensor with this telescope, then this object, I mean, the disproof of the telescope conjecture shows that this is not Kn plus 1 local. But on the other hand, the other thing that you're comparing it to, so the thing that you'd be comparing it to, which is TC of BPN to the BZ, it turns out that this one is Kn local, Kn plus 1 local. And so, they can't be equivalent as spectra, but somehow their homotopy groups are still the same. And so, yeah, it's just, so they're not, so they're sort of they only have isomorphic pi stars. Okay. And so let me explain, how could this possibly be? Like, how would you get something like this? And the key point is that what is true is the following. What is true is that instead of inverting Vn plus 1, if you mod out by some power of Vn plus 1, then you can get an equivalence at the level of spectra. And the point is that you can recover the homotopy groups from the homotopy groups modulo a sufficiently large power of Vn plus 1. So let me explain what I mean by that. So here's just a basic lemma that we can very quickly check. So suppose you have X, which is a bounded below spectrum, and you have some self-map of positive degree from X to itself. So V is positive degree. And let's say that X mod V is bounded above. So the kind of thing you should imagine is that X is something like TC of BPN fixed points by Z tensored with Vn plus 1. You should imagine that X is something like that, and that this map V is like some power of Vn plus 1. That's what you should imagine. So then the lemma is that this implies that the homotopy groups of X after inverting Vn plus 1 can be recovered from the homotopy groups of X modulo V to the A for A sufficiently large. Okay? And this is sort of a natural recovery of this. You can naturally recover this from that. Okay? And so the proof is not hard. So the proof is just that, well, the fact that this is bounded above is telling you that pi star of x, the multiplication by v map, which goes to pi star plus v of x, is it's an isomorphism for like in large enough degrees. So for example, when star is at least n for some large n. And then our other hypothesis is telling us that pi star of x, so the other hypothesis tells us that the other hypothesis is that x is bounded below. And that will tell you, that plus the fact that v is positive degree, will tell you that when you take pi star of x and you look at the map to pi star of x mod v to the a, just because v to the a has too high degree, this is an isomorphism for let's say star at most n plus the degree of v, if let's say a is sufficiently large. So you can just make a as large as you want, such that this will be an isomorphism in any finite range of degrees. And so in particular, you can make it in this range of degrees. And then the point is that using this, you can see that you have enough information about the homotopy groups of X such that this periodicity, the fact that the multiplication by VMAP is an isomorphism in large degrees, tells you that you can recover the homotopy groups after inverting Vn plus 1 just by looking at the homotopy groups of this thing in a certain range and then just periodizing it with respect to Vn plus 1. Okay. Okay, so yeah, so applying this to TC, what you see is that sort of the key thing you want to show, like even though these things are not equivalent, it would be enough to show something like THH of BP and fixed points by Z tensored with a type n plus 2 complex. It would be enough to show that something like this is bounded and equivalent to the same thing with the trivial action. Okay, so the what was I gonna say? So here's the key claim. Here's the key claim that we're gonna need, and I'm gonna slightly modify this claim later. But here's sort of the preliminary version of the claim. So the key claim that we're gonna need that I'm not gonna prove today, but I'll say something about next time, is that this THH of VPN fixed points by Z tensored with a type n plus 2 complex, we want to show that this is bounded. So in other words, we want to show we want to know that this VPN fixed points by Z satisfies the Lichtenbaum-Cohen property of height n. Okay. And the point is that if you assuming this claim, using this claim, it's sort of enough to show the following. It's enough to show that this THH of BPN, after you take the fixed points by Z and you tensor with this maybe a type n plus 1 complex modulo some power of Vn plus 1, it's enough to show that this is isomorphic to the same thing with the trivial action. And you need a little bit more than this, and I'll explain what that is. So there's a ring that acts on both of these objects, namely, so if you take any ring, and you take the fixed points by some Z action, there's a map from the fixed points of the sphere by the trivial Z action. So S to the BZ maps to this, and it acts on this ring. And so all of these things have an action of THH of the sphere to the BZ, which is what we studied in the second lecture. So we actually want this isomorphism as modules over this ring, okay, in cyclotomic spectra. And so the point is that if you know this isomorphism as modules in cyclotomic spectra, then you in particular get this isomorphism by taking just applying TC and this lemma about recovering the homotopy groups after inverting Vn plus 1. And then you can also recover this isomorphism, essentially because this module structure tells you something about the co-assembly map. Namely, the co-assembly map it comes from tensoring over this ring with just the map to S to the BZ itself. So you recover this isomorphism compatible with the co-assembly map. Okay, so I want to now go into why is this kind of isomorphism true. And so we've already used the Lichtenbaum-Coulomb property once to sort of say that you can recover the homotopy groups after inverting some Vn plus 1 by looking at it modulo Vn, some power of Vn plus 1. We're going to actually use it again in proving this isomorphism. And the point is that if you just choose some fixed Adams operation, this isomorphism might not be true. And so the key observation to making this kind of observation to making this isomorphism true is that you can replace Z with a sufficiently small subgroup P to the KZ, and if you make K sufficiently large, then this isomorphism will get closer and closer to being true, and then there will be some kind of compactness argument that tells you that it actually had to happen at some finite stage, that it was literally, they were literally the same. So let me try. So the claim is that if you replace Z with P to the KZ for K sufficiently large, then we can make this true. We can make this isomorphism true. Isomorphism true. Okay, so so why is that? Why is that the case? Why does replacing Z with P to the KZ help? So it's because of the following notion. So it has to do with the fact that all of the actions of Z that we're considering are locally unipotent. And so I want to explain what that means. So a locally unipotent object, what does that mean? So a locally unipotent object, so spectrum, let's say, with an action of the integers, and let's say it's P complete. It is one satisfying the following equivalent conditions. And I'm not going to prove that these are equivalent, but I'll just say that it's not terribly difficult to do so. So the first condition is maybe the reason why it's called locally unipotent, or one of the reasons. So if you look at pi star of x mod p, then this has an action of the integers, and you want this as a representation of the integers. You want this to be built from trivial representations. Under colimits and extensions. Okay. So it's saying, the action might be non-trivial, but it's pretty close to being trivial. Like it's sort of at every point, it's finitely far away from being trivial action. Okay, and then the second equivalent condition is the following. So you can take the fixed points of x by p to the kz, and you can just take the co-limit as k goes to infinity. And the claim is that that is just x itself in p complete spectra. Okay. Um, and then the third condition is well, okay, maybe if this doesn't seem reasonable to you, you can try to convince yourself that this is true in the case of a trivial action. Why is this true in the case of a trivial action? Okay, so the third condition is that if you take x and you take the fixed points by z, well, that's a module over the sphere, and you take the fixed points by the trivial action, and you can base change to the sphere to some uh, subgroup. And I'm going to allow uh, k to be possibly infinity, in which case the subgroup is just the zero subgroup. And this condition is that this base change is in fact just x to the fixed points by the subgroup. And then the fourth condition is that x is in, oops, it's in the stable localizing subcategory generated by the sphere with the trivial action. Okay. And so it's built out of trivial representations. Okay, so these are all equivalent. And so, yeah, so this condition is sort of saying that if you let k get very, very large, then you're sort of, I guess you're approaching x, which is something that clearly just depends on the underlying spectrum of x. So it would be the same, for example, if x had a trivial action. Okay, so now one of the points about this Adams operation, so there's this action, this Adams operation on BPN, and it acts on pi star by some constant, like on each homotopy group, it multiplies by a number, and that number is 1 mod p, right? So multiplication by constant that is 1 mod p. And so what you learn from the first criterion, this first equivalent condition, is that BPN with its action of the integers is locally impotent. And so what does that tell us? It tells us that if you take, so THH is something that preserves filtered colimits. And so what you learn is that if you take the colimit of this THH of these fixed points, then you just get THH of BPN. Okay. And so this is true, and so we can also just tensor it with our favorite type n plus 1 complex. And I'll just give this a name to shorten the notation a little bit. I'll call it W. So I'm just going to tensor this isomorphism with W. And so now here's the key point in proving this equivalence with the trivial action. The point is that you should let's pretend that so what are we trying to prove maybe? What are we trying to prove? We're trying to prove that THH of BPN tensored with to the BZ, which is the same thing as tensoring with THH of the sphere to the B P to the KZ. What we want to prove is that this object is isomorphic to THH of BPN, the H P to the KZ. Okay. And the problem is that we don't even have a comparison map. There's not even a comparison map. So there's a map from this ring into THH of BPN to the HP to the KZ. That's because this even acts on this, and there's a unit. But we don't have a map in from THH of BPN. And so what you kind of want is you kind of want like a splitting of this colimit. So if, for example, you knew that this was compact, if this was a compact object, then the fact that this filtered colimit is this compact object would tell you that there's a splitting at some finite stage. So this colimit splits at some finite stage. So yeah, we want a splitting we want a splitting map from THH of BPN into THH of BPN, the HP to the KZ for K sufficiently large after tensoring with this W. And so let's call this splitting map C bar, and let's call this hypothetical comparison map that so if you had the C bar, then you could just tensor with this object, I'll give this a name too. So I'll call this WK. And so if you have a map like this, then you can just tensor with this object to get a map that I'll call C. So if you want to produce this comparison map that we want to be an equivalence, the key thing that you have to do is produce this map, C bar. And so the question is really, why does C bar exist? And so again, as I told you, if THH is compact, if this object was a compact in cyclotomic spectra, then it would be obvious why such a map exists. But THH of BPN, fixed points by P to the KC, tensor with W, or sorry, let's not take the fixed points right now. Yeah. So this object isn't compact in cyclotomic spectra, so you can't run that argument, but it's almost compact. It's what's called almost compact. So let me explain what almost compact is. So here's the definition. So let X be an object inside some category, which is going to be, let's say, stable infinity category with a T structure. And so what does compactness mean? Compactness means that if you take the mapping spectrum out of X, then this should commute with filtered colimits. That's what compactness means. But X is almost compact if the mapping spectrum out of X commutes with filtered colimits of uniformly bounded objects. Okay. So maybe to give you a feeling for what this notion is, let's think about what this means in the category of P-complete spectra. So if C is P-complete spectra, then X. So what this is saying is that you want HOMs out of your spectrum to commute with filtered colimits, but only for truncated objects. And that's exactly saying that your object should be sort of approximable by compact objects in some range of degrees, in any finite range of degrees. And so that's equivalent to so X is almost compact if and only if X is bounded below let's see. pi star of x is finite for each star. And let's see, is that it? I think that's it. Yeah. So if you have these two conditions, that's what it means to be almost compact in p-complete spectra. And here's sort of a key proposition, which is some fact about cyclotomic spectra. I mean, I'm not going to prove it, but it's just a general fact about cyclotomic spectra. It's in the telescope conjecture paper. So the proposition is that a cyclotomic spectrum, which is p-complete, is almost compact if and only if the underlying spectrum is. Okay. And okay, so in particular, it's not hard to see that THH of BPN is almost compact in p-complete spectra. Like it satisfies this property. That's not so hard to verify, just from the fact that BPN is connective in a finite type. Or sorry, this is after you tensor with some W. So what you learn from this proposition is that this is almost compact. And so the point of this, well, sorry. So the point of this almost compactness condition is that if you whenever you want to use compactness, you're allowed to replace it with almost compactness so long as everything that's showing up is uniformly bounded. And so we wanted to apply compactness to this colimit map. And so if we knew that all of these things were uniformly bounded in the cyclotomic T structure, then you could use the fact that this is almost compact to produce a section at some stage, at some finite stage. And so that's actually the more refined version of this key claim that we had earlier. So the key, I'll call it key claim prime, maybe, which is that what you need to know is that this THH of BPN fixed points by P to the KZ and tensored with W, you want to know that this is uniformly bounded. In K, in cyclotomic spectra. Okay, so you want sort of the Lippmann-Cullen property for all of these rings in a way that's uniform in K. And I mean, in practice, that ends up not being more difficult than just proving it for one of them. It's just a matter of keeping track of the parameters that show up. Okay, so this is the key claim. And so how does it help us? Well, it allows us exactly so using almost compactness, you can exactly produce this map C bar that we wanted, and hence you can produce this map C. So this gives us, we get a module map over this ring. This is THH of sphere to the, recall that this is THH of sphere to the V, P to the KZ. You get a module map over this from THH of BPN to the BP to the KZ to THH of the non-trivial action after you tensor with W. Okay. And now the key thing that remains, one of the key things remaining is to prove that this map is an isomorphism. Okay. And this is actually also a situation where Lippmann-Cullen property is going to help us. But we need sort of a bit more than that. So we're gonna use some nice properties about the ring of continuous functions on ZP. So let's recall what this WK is. So this is what we computed last time. So it's THH of this ring, which is it's the sphere to the B p to the kz tensored with the spherical width vectors of the continuous functions on p to the k zp. Okay, that's what we saw last time, and so in particular, what that's saying is that this ring of the ring of continuous functions on p to the k zp, maybe with coefficients in zp, which is like pi zero of this ring. Pi zero of this ring acts on any module over this ring. And so here's sort of just a key, it's a simple algebraic lemma about modules over this ring. So it's the following. So it's very much related to this. It's about checking something's an equivalence. So the lemma is that if you have a map of let's say finitely presented continuous functions on ZP with coefficients in ZP modules. So this is really just pi naught of the spherical width vectors. Sorry, let me put a p to the k here. So if you have a map of finitely presented modules over this ring, then it makes sense to talk about f restricted to 0, which is sort of base changing from this ring to just continuous functions on a point. So you can assume that, let's assume that f restricted to 0 is an isomorphism. And let's also assume that m and n are p-power torsion. So they're rationally trivial. Okay. Then the conclusion is that this isomorphism that you have at the point 0 actually sort of spreads out to some neighborhood of 0. So you learn that f restricted to p to the k prime zp is actually an isomorphism for k prime sufficiently large. Okay. So why is this? So the proof of this is not so hard. So the key thing to observe is that this ring, it's really if it's oops, sorry. Like this category of p-power torsion finitely presented modules, it's an abelian category. And so what you learn is that the kernel, so the kernel of this f, it's finitely presented. And you also know that the kernel of f restricted to 0 is 0 because this map was an isomorphism at 0. And so, well, there are finitely many generators. So let's choose our generators like x1 to xn. And you know that x1 to xn becomes 0 at the at 0. And so what that tells you, well, what am I saying? So the point is that the fact that x1 to xn were 0 at the origin and p-power torsion, the fact that continuous functions on z, okay, sorry, I should write it the following way. So you can take the colimit over k of continuous functions on zp with coefficients in z mod p to the n, p to the m, and that, sorry, let me, sorry, I'm just getting my notation confused a bit. So the point is that the co-limit of the restriction maps, where you take a function on ZP and you restrict it to PZP and then P squared ZP and so on, you keep restricting. The co-limit of all those maps is just Z mod P to the N. And that co-limit map is given by restriction to the origin. Like if you restrict to smaller and smaller subsets, the co-limit of that is just restricting to the origin. And so the fact that these elements became zero in the co-limit, like they became zero after you restrict to zero, tells us that in fact each xi was already zero at some finite stage, because these are just elements. And tensoring with the filtered co-limit, tensor products can be with filtered co-limits. So you learn that xi was already zero for if you restrict to p to the k zp for k sufficiently large. And so it tells you that this is injective for k sufficiently large, for k prime sufficiently large. But then the same argument works for the co-kernel. So similarly for the co-kernel. So you learn that it's an isomorphism. Okay. So this is just some algebraic lemma about modules over the string. And what it tells you is that having an isomorphism of sort of finitely presented modules can sort of spread out to some neighborhood of the origin. And so we want to apply that in our situation. So we have this map, this comparison map. So if you look at street restricted to zero, what is that map? Well, this thing restricted to zero is just Bpn to the Bp to the Kz, tensor with W. And the right-hand side is Bpn to the Hp to the Kz, tensored with W. So it just gets rid of the THH, essentially. That's what this restriction to zero does. And so, well, wait. So I guess the claim is that this map is easy to see as an isomorphism for k sufficiently large. So I can try to explain why. So what you can observe is that these are, as k varies, these are almost compact. They're almost compact. And as they're varying, so recall this sort of third condition that I'll scroll back up. So we had this condition that tells one of the equivalent conditions for being locally unipotent is that taking the fixed points by a smaller subgroup is the same thing as just base changing along a ring map. That was one of the equivalent conditions for being locally unipotent. And so going back over here, what we learn is that as these maps, as we vary this k, we can basically look at we can just look at our map C tensored over so we're looking at the map C tensored over S to the B P to the K of Z with S to the B P to the K prime of Z. And so the point is that if you have, if you take the co-limit as K prime goes to infinity, if you take the co-limit over K prime of all of these maps, you just get the map from, you just get the identity map from Bpn to itself. And so that's clearly an isomorphism. And so what this is saying is that you have a bunch of bounded, almost compact modules over a ring, and you're base changing them along some filtered co-limit that remains bounded. And that filtered co-limit, in that filtered co-limit, you get an isomorphism. And so the point is that if you have a compact module over, if you have two compact modules over a ring, and you know that in some filtered colimit of base changes, they became equivalent, then that equivalence has to happen at some finite stage. And so the same principle applies for almost compactness. So if you have two almost compact bounded modules and they become equivalent after some filtered colimit of base changes, then that had to also happen at some finite stage. And so what you learn is that, so you learn that this C tensored over S to the B P to the K Z with S B P to the K prime of Z is an isomorphism for K prime sufficiently large. And then using this lemma, sorry. So then using the lemma, you learn that THH of BPN to the B P to the KZ, if you tensor it with W, well, we were interested in this comparison map to the same thing with the non-trivial action. And you learn that this comparison map becomes an isomorphism if you restrict to P to the K prime ZP in low degrees. So the point is that you can just look at this map on homotopy groups, and you can apply this lemma up here. You can apply this lemma up here to this map on homotopy groups, and you learn that this map is sort of an isomorphism in low degrees if you make K prime sufficiently large. So in other words, this map has highly connected, as connected as you want, so long as you, but the connectivity will depend, this K prime will depend on how connective you want it to be. So it has highly connected fiber for K prime sufficiently large. Okay. Okay, so that's pretty close to what we wanted, but not really. We didn't want to restrict. But the point is that the restriction isn't so bad because, in fact, we were like, if you look at the functor that's given by base changing from one of these rings to one of these other rings, this base change map factors through the restriction to P to the K plus P to the K prime ZP. And so what you learn then is that THH of BPN to the B P to the K prime Z is actually isomorphic in some low degrees to this THH. You learn that this map after you tensor with W has highly connected fiber. For K prime sufficiently large. And now again, we're going to use the Slicht-Malin-Cullen property. So the point is that both of these objects, both of these are bounded above in cyclotonic spectra. And so if the fiber has connectivity that's like strictly larger than the bound on both of these cyclotonic spectra, then the fiber had to be zero. If you have two bounded objects and the fiber is highly connected, if it's too highly connected, then it just had to be zero. And so what you learn is that, in fact, the map is isomorphism. So it's in fact an isomorphism of modules over the string wk prime. Okay, and so let me just recall what this brought us. So the point is that having this isomorphism of modules, what that tells us is that you can. So what is this W? It's a type n+1 complex modulo some power of V. And so what you learn is that when you take THH of BPN, fixed points by this trivial action, we learn that there's an equivalence between that and THH of this non-trivial action. And you can apply TC to both of these objects. And there was this lemma from the beginning of the lecture that said that from TC of both of these objects, you can in fact, if A is sufficiently large, you can recover the TC after inverting V, which is that's the telescopic homotopy groups. And so this isomorphism is good enough to give the first equivalence in the square that we wanted. But in fact, the fact that it's an isomorphism of modules tells us that we actually have a compatible square as follows. We have this square. And then applying the same reasoning to this whole square gives us exactly the original square that we wanted to prove. Existed. So, okay, so the conclusion is that we get this isomorphism of cyclotomic spectra, the square, and then taking homotopy groups at the level of TC of these objects, you can recover the original square that we wanted to prove. So you can extract pi star of TC tensored with Vn+1 and then inverting V from this. Okay, yeah, so that's all I wanted to say today. So, but yeah, the point was that we can use this Lipton-Cohen property. It's very powerful to prove this kind of square. It was sort of used several times in the proof. And I'll go next time into how do you actually prove Lipton-Cohen theorem for these things.